In this section, we're going to look at visualizing a distribution. Now, a distribution is a set of values and the frequency of occurrence. So what that means is we have a bunch of numbers and how often these numbers show up in the distribution, in the list of numbers. So let's go ahead and take a look at something that's a fairly common example. Let's say you did a survey of some kind on the reverse classroom, and the scale was from 1 to 5. 1 is I strongly dislike, 5 is I strongly like, and this is an actual survey that was done. So let's take a look. We see from the graph that there's a lot of people that like it, maybe not strongly like, but like, and then 3 and 5 are kind of the runners-up behind 4. Not a lot of people that dislike it, but a few people that strongly dislike it, which is kind of interesting. So we have this one major peak over here, and then we have a minor peak over here. Now, the reason that we like to visualize a distribution is because if we were just asked, well, what was the mean score for reverse classroom? We would probably get, oh, well, it was 3.8. And we would lose all of the information about this other group kind of down on one end that wasn't as strong, but is clearly a significant group whose needs are probably not being met with this method of instruction. You also lose some of the information about where the peak is. For all you know, you could have peaks at 3 and 5 and not many people moderately here, or you could have it closer to 4 like it is. So visualizing the distribution gives you a lot more detail in a very concise, clear graph that you would lose if you just looked at the mean, the median, or the mode. So let's take a look at the results of a survey question on how many siblings you have. If you get a list of numbers like this, it's really hard to process and do anything with. You have 2, 1, 2, 1, 3, 1, 2, 1, 4, 1, blah, blah, blah. Very hard to deal with. So what we're going to do is we're going to use something called a dot plot. The reason that you would use a dot plot is our list is relatively short, and this is in comparison to some other graphing techniques I'm going to show you in a second. The list is relatively short, and the data set is discrete. And what I mean by discrete is that the possible values are integers. They're things that can be counted. So we have 1, 2, 3. Those are the results of how many siblings you have. You can't have 4.5 siblings or 4.59423 siblings, for example. It's a discrete number of choices. So when you have that, a dot plot's a good thing to do. So when you create a dot plot, the way that you do this is you look at each number in the list and you put a dot over it. So to show that example here, we have a 2, so we put a dot over 2. We have a 1, we put a dot over 1. We have another 2. Now when you have the second one, you just put the dot on top. You stack them. And in the end, it's going to start to look almost like a bar graph. So I'll go ahead and skip ahead here. So once you finish your dot plot, you can see that there's a pattern here. It seems like 1 is a very strong response. Most people have 1 sibling. And then it kind of tapers off downwards, and there's a small number with 0 here on the other end. So when you create a dot plot, it gives you a quick visualization of your data. In this next example, we have a list of average grades for a semester. We have 89.1, 72.2, and so forth here. This time around, we're going to use something called a stem plot to visualize the data. And here's why. The list, again, just like the first list, was relatively short, but less than 25 responses. Here it looks like we only have about 9 or 10. And this time, though, the data set is not as discrete, it's more continuous. And when I say continuous, it means that all possible values may occur within a given range. So any possible number between, let's say, 60 and 100 could come up as an average grade. Now, because these values are all rounded to the 10th, it's not truly continuous. It is still technically considered discrete because you could count up every possible value. But as you can see, there's many, many more choices. It's tending towards being continuous. Whereas the previous example, there were only really 6, 7 choices. This one here has many more possible values that you could get. So let's go ahead and take a look at what the stem plot is. Sometimes it's also called a stem and leaf plot. What we're going to do is on the left side, for the stems, we're going to take the tens place. So we have some numbers in the 60s, some numbers in the 70s, some in the 80s, some in the 90s. So we have 60, 70, 80, 90 over here on our stem. On our leaf, let's go ahead and start with our first value. Our first value is 63.5. So if we have a 60 over here, we put the 3.5 over as our leaf. Same thing with the 70s. We have a 72.2 and 79.9. And I'm going to list those in order. First one's going to be the 2.2, and the second one's going to be the 7 or the 9.9. And you do that for all of those. Again, always listing them in numerical order. And as you can see here, by looking at the stem and leaf height, first of all, you could figure out what all your values are. Here I have a 60, here I have a 3.5, so I know one of my numbers is going to be 63.5. Same thing here, one of my numbers is going to be 88.6, 89.9, and so forth. So from looking at this graph, I can see what all my numbers are, but I can also see a general trend. I can see, okay, it seems like most of them are clumped up in the 80s, and trailing off towards the 90s and 70s, and then trailing off even farther if you get into the 60s. Now, you don't have to break it at the tens place. If you had a smaller set of numbers, let's say numbers were ranging from 1.1 to 5.10 or 5.9 or something like that, then you might just have the ones place over as the stem and the decimal as your leaf. So it all depends on the numbers you have, but in this particular example, breaking at the tens place is a good place. Here's another example. We have a list of average grades for the semester, just like we did before, except this time the numbers are a little bit closer together. Our lowest value here is a 70, and our highest value is a 95. So if we were to make a stem plot the way we did before, we would end up with, okay, we have our 70 and our 79, so we'd have a 0 and a 9. This time I don't have any decimals, but so we just have 0 and 9. For 80, we have a few numbers in the 80s, 82, 85, 87, and so forth, and a few numbers in the 90s. Now I can see a general trend here. If I look at this, I can see most of them are kind of clumped in the 80s, kind of trails off into the 90s, and farther down into the 70s. But because it's all so bunched up, I can't get a very good idea of really what's going on in detail. So when we have so much clumping like that, when it's only split into 3 stems, we might split the stem. And so here you can see I split it 70 into 2 separate pieces, 80 into 2 pieces, and 90 into 2 pieces. And instead of going from 70 all the way up to 79 here, I'm only going to go 70 to 74 in this first one, and then I'm going to go 75 to 79 in the second one. And so really, I'm just breaking it up into 2 equal-sized groups. So here I had a 70 and a 79. So the 70 would go in the first one, and the 9 then would go into the second one. Over here in the 80s, I had an 82. That would go in the first one. But then all these other ones, 85, 87, 88, 88 again, and 89, would all go in the second one. So you can see that breaking this up allowed me to see that most of them are actually in the high 80s, not just anywhere in the 80s. And then again, the same thing with the 90s. And you can see here, most of the ones in the 90s were actually in the low 90s. So by splitting the stem, instead of just getting this general trend, I can see that it's actually much closer to a trend like this, where the peak is in the high 80s, not in the middle of the 80s. Now let's take a look at an even larger list of average grades for the semester. This time we have 39 different numbers. Now when you start to get to numbers like that, stem plots start to become less feasible. So we have a new thing that we're going to use called a histogram. However, before we do that, we need to put our data into chunks, just like we did with our stem plot where we put it into chunks, except this time we'll use a table. So for example, let's decide that 60 to just under 65 is going to be one chunk. How many numbers fit in there? Well, let's take a look. Looking for our numbers in the low 60s. There's one in the high 60s there. We have a 64. Okay, that's the only one. So we're going to have one of those. And then you go on, 65 to 69. We saw we had a 68 in here, but I think that's it. So then we'll just have one of those also. And you go on and keep doing that and keep putting them into bins. And you'll notice that at first it might seem a little arbitrary of why I picked 60 to 65, 65 to 70, and so forth as my bucket sizes, my bin sizes. But what you're usually striving for is to try to get approximately 8 groups. Now this time I happened to get exactly 8 groups. That worked out real nicely, but anywhere from 6 to 10 usually works, and I'll show you what that means in a second. Let's go ahead and take a look at our histogram. Whenever you make a histogram, you take your bin sizes that you have, and you put the edges of your bins on your x-axis, and then the frequency, how many times those numbers come up, how many numbers are in each of these bins, goes up on your y-axis. So the first one here, 60 to 65, and remember it's just under 65, so that's why I wrote it as 64.99 to remind you that. There's exactly one value, so we'll just make a bar with a height of 1 that goes from here to here. Note that I didn't put the label directly underneath the bar like that. The labels sit right at the border on the edges of each bar. Again, 65 to 69, bar height of 1, so same thing. 70 to just under 75, we have 2 values in this data set, and you keep doing that. Next one, we happen to have 7 values in the data set, so that bar is much larger, and you do that all the way through. And then just as a reminder, the reason I color-coded these is just so you could match up with times where x is greater than or equal to 60 and x is less than 65. Well, we had that value of 64, and that's where that number 1 came from. Same thing with this 80 to 80, just under 85 bar. And when you do this, you can start to see, just like the other graphs, a general pattern of your data. And now this little line that I'm drawing over it, and you can see that I'm clearly rounding things off a little bit, but that's the overall basic pattern that you're seeing. If you had, let's say, 30 different bars here that you were breaking it into, it would be too choppy to actually get a really good idea of what the pattern looked like. And if you had too few bars, let's say you only had 4, it would again be hard to see the trend, just like when we had the stem plot with only the 3 groups. It was too clumped up to really see enough detail. So that's why we try to strive for approximately 8 bins when we're making a histogram. Now on this page, we're going to take a look at something called a cumulative frequency plot, which is really just a histogram totaled up with all the values below it. So cumulative frequency is the sum of the frequencies at or below the given value. So if we're going to find the cumulative frequency of 60 to 65, well, there's 1 at or below 60 to 65. But for the next one, there's 1 plus the one before it, 2. For the next one, how many are at or below this group here? How many are at or below this bin? Well, we have the ones in that bin, plus the ones below it, and the ones below that. So this one is going to be 4. And all we're doing for the cumulative number is we're just taking all the numbers, taking the number itself, plus all the quantities in the bins below it, and adding them together. And if you do that, you're going to get this little plot of numbers. So if this was our original histogram, our cumulative frequency plot is going to look something like this. And if our conditions before were x has to be greater than some number and less than some other number to be in here, now it just has to be less than the upper range. So for the purple bar here, as long as x is less than 85, that'll tell us how many numbers that fits. How many numbers are less than 85? Well, if you look at this graph here, it's approximately 17. And if you go to our big list of numbers here, you would count up 17 numbers that are less than 85. So that's a cumulative frequency plot. You'll notice that with a cumulative frequency plot, it's always going to start near 0 and end near 100%. So it's always going to have something like that. This page we're going to look at something called a density curve. And a density curve is what I've been basically sketching on all of these graphs. Whenever we want to kind of smooth things out to find the general pattern, we're drawing a density curve. And so, again, this is not perfect, but that's part of the idea. Is I'm just trying to smooth out some rough data. So a density curve, technically speaking, if you took this histogram and you made these bins very, very small, let's say you tried to make it so that the bins got as small as possible, something very, very thin like that, and then you had tons and tons of data so that you could have it perfectly fit the distribution, then you would be able to complete a density curve on that data and have an exact value. So whenever we do it for the histogram or the stem plot or the dot plot, we're really just approximating what it might be like. Last thing we're going to look at is skewness. It's a measure of how symmetrical a distribution is. So let's go ahead and pull this away here. I just quickly drew some sketches on here, and I'm only going to take a look at a few of them for the moment. When something is roughly the same on both sides, we call that symmetrical. And when it has only one peak, we call it unimodal. So the symmetry versus skewness is the first thing we look at, and then how many peaks is another. This graph over here, you can see, has a big long tail on one end, and most of the data is clumped off to the side, not in the middle. So we call that skewed, and in particular, this one, because the tail is on the left, we call it left skewed. And because there's one peak, we call it unimodal. This one over here, tail's on the right. Again, the data's off to the side, so this one is skewed right, and once again, unimodal. An example of something that's symmetrical just like this one, but has two peaks, we call that bimodal. And if it had three peaks, it would be trimodal, and so forth. This one down here is something you won't see very often, but there's two peaks, and most of the data is off to one side. So we say that this one is skewed to the tail, skewed to the left, but bimodal. And this final one here, because all the data is the same, we ignore all of this and just call it a constant function. And that's all for distributions.